Yeah, welcome everyone. It's a great pleasure to organize these talks, and we start with Andrzej Grzesik, which many of you might know from many papers involving, let's say, flag algebras and related topics. And I'm curious what he is going to speak about today. And without any further ado, Andrzej, your go.
Thank you very much. Thank you, Stefan and Felix, for invitation to this mini symposium, and of course to Andrzej for organizing the conference. I hope you can see my slides now. Perfect. If you would like to ask any questions, feel free to interrupt me at any moment. I'm happy to stop and explain if something is not perfectly explained. So really, feel free to interrupt me. And I will be talking about general Turan problems for cycles, and this is based on a joint work with my master's student, Mateusz Górski. Yeah, so you probably all know in this company what the Turan problem is, but let me briefly explain. So in a Turan problem, we are asking for the maximum number of edges in an n-vertex graph which does not contain a specific subgraph F as a subgraph, not necessarily induced. Yes, so I'm forbidding some subgraph F, and I'm asking what's the maximum number of edges. And this is like historically very explored area. From 40s, we already know that if a graph is not bipartite, then from Erdős theorem, this constant will not be 0, but some positive number, and it gives us what this maximum number of edges in an n-vertex graph is. So we know it's quadratic, and we know what's the exact constant here. Yeah, so basically everything is known if our graph F, the forbidden graph, is not bipartite. When it's bipartite, here we get just 0. So we know that the order of magnitude is smaller, but even finding this order of magnitude is a hard problem for many graphs. So not much is known, and if you are interested in the topic, there is a very good survey paper available on internet. It's called just the history of the generated Turan problems. And in case of cycles, which is the topic of my talk, we know that we know the correct order of magnitude only for 4 cycle, 6 cycle, and 10 cycle. Every other even cycle is we don't know even the order of magnitude. So you can imagine this is a very simple graph, and we still don't know, for example, for 8 cycle, what is the maximum number of edges, even in the order of magnitude. And the generalized Turan problem is a similar concept, but we are not maximizing edges, but maximizing copies of a particular graph H. So now we have 2 parameters. One is the forbidden graph, and the second one is the graph that we would like to maximize. So if this H is just the edge, the K2 graph, then we have the standard Turan problem. But for H, we can take any other graph, and we want to maximize number of copies among graphs which does not contain our forbidden graph. So historically looking, for cliques, it's known since 60s in let's say West world, and since 40s in East world. It was independently determined, and next results are basically this conjecture, Erdős pentagon conjecture from 80s, which was saying that if I forbid triangles and I want to maximize 5 cycles, then the best is n/5 to the 5th power. And this number comes from the fact that we can take a blob over 5 cycles. So I just take 5 blobs, each of size n/5, and connect all possible edges around. Yeah, so this is like sounds like a easy conjecture, but it was open since 80s. and we only knew some bound with multiplicative error terms of like 3% more due to Jerry and also from 80s. And since this easy case was we were not able to solve, basically nothing was going on the topic of generalized Turan problems. And then two things happened. One was the solution of this conjecture in 2012. I will tell more about this solution. Now, maybe just let me add that this was done using Rasborov flag algebras, and the method can be used in many other problems like that. So it was very powerful for the topic. And the second thing is a paper by Alon and Schickelman from 2016, which start investigating those generalized Turan numbers for specific graph classes of graphs, natural classes of graphs, I would say, like triangles, complete graphs, or complete bipartite graphs, or trees. And since then, which is like 5 years, lots of papers appeared on the topic. This paper had more than 100 citations. So you can easily see that really lots of people are exploring this area of generalized Turan numbers. And what's important, we need to decide what's the split between dense cases and sparse cases, right? In the standard Turan problem, we know that for non-bipartite graphs, it was easy. And for bipartite graphs, it was degenerated, sparse, and less than constant times n-square edges, and it was hard. So what's the split for the generalized Turan problem? So we can easily see that if the forbidden graph is not a subgraph of a blow-up of the graph that we want to maximize, then this extremal number is of the same order of magnitude as it can be. Let me recall that the blow-up is just, if I have a graph, let's say this is my graph H, then blow-up is just take a block for each vertex and connect all possible edges according to the edges in graph H. Right, so if I take such a blow-up, it has maximum possible order of magnitude, which is n to the power of number of vertices, and it does not contain the forbidden graph F, if we have this assumption, right? So this is easy. But if F is a subgraph of a blow-up of the graph that we want to maximize, then from easy counting or graph removal lemma, we can see that the order of magnitude will be smaller, right? So this is the split between the dense world and the sparse world. Okay, so as for the Turan problems, in the dense setting, we know the order of magnitude, and our problem is to determine what's the constant, right? What's the constant by the n to the power of the graph. While in the sparse setting, even finding the order of magnitude might be hard, right? As I said 2 minutes ago, even for cycles, solution of the standard Turan problem is a hard task. Okay.
Andrzej, can I ask a quick question?
Mm-hmm.
So here epsilon is a constant, the positive constant that depends on the two graphs. So
yes.
So you can definitely do it without the graph removal lemma, right? This time.
Yeah, can you without
you can do it without the graph removal lemma then, right?
Yeah, that's true. Yeah, you can just prove that you can go below. It will be definitely not the maximum possible order. Definitely, it will be smaller order of magnitude.
Sorry, what is sparse setting?
Oh, yeah. So basically, this is what I define by sparse setting. Because, like in the edge case, it's a standard Turan problem. By dense graph, I mean graphs which has theta of n-square edges, and sparse graph has like zero density of edges, smaller order of magnitude. And for the generalized Turan problem, if we have n to the number of vertices in H, possible copies of H, then this is a dense case for me. And if we have like strictly smaller, then this is sparse setting. Okay, there are no more questions. Let me go to the main topic, which is the generalized Turan numbers for the cycles. So what do we know for cycles? Yeah, the split between dense and sparse. When some forbidden cycle of length L is a subgraph of a blow-up of the cycle of length K that we want to maximize. Of course, when the cycle that is forbidden is of even length, then it appears in a blow-up of any other cycle, right? So this will be the sparse setting. But also, when they are both odd and the forbidden cycle is longer than the smaller cycle. Yeah, this is easy to observe because in a blow-up of a small odd cycle, you will find any longer odd cycle because you can just go between the blocks there and back. Okay, so yeah, this is the split between the dense setting and the sparse setting, and what's known. So in the dense setting, we know the order of magnitude because we can just take a blow-up of a K cycle. And in the sparse setting, in every case except triangle, so K at least 4, the order of magnitude was determined by Dijboliner and Shapira last year, and independently in this harder even case by Gerdner, Jerry, Metuku, and Wieser. While for triangles, which is K equals 3, we have bounds that depends on the standard Turan number of even cycles. Yeah, so if you make any improvement for standard Turan problem for even cycles, we get an improvement here. Yeah, so we can say that basically the order of magnitude is known. I can imagine that if somebody improved the order of magnitude here, you can also improve the order of magnitude for even cycles in the standard problem. Okay, so let me now say separately what's known in the dense setting and what's known in the sparse setting. In the dense setting, if they are both, if the graph that we want to maximize is even, and the graph that we are forbidding is odd, like odd size cycle, then the problem is very easy because the maximum is in the blow-up, in the balanced blow-up of a bipartite graph, balanced blow-up of an edge, which is complete bipartite graph. Yeah, such a complete bipartite graph does not contain any odd cycles, and it has quite many even cycles. And you can prove that it's really maximizing the number of even cycles for whatever size you want. So this is easy. And the second case in the dense setting is when both K and L are odd, and the cycle that we want to maximize is bigger than the cycle that we forbid. So here, the first case is we forbid triangles and we maximize pentagons, and this is exactly this Erdős pentagon conjecture from AD. So as I said, this was solved in 2012 by me and independently by Hatami, Klatkikal, Norin, and Dasborough. But the problem is that we both use this computer-assisted method of flag algebras, and this is problematic because one cannot generalize it for a longer cycle, since it requires generating all graphs of specific lengths, and maybe for 7 cycles one can use it, but 9 cycles are out of reach because there are too many graphs on 9 vertices, and it creates too big space to use. Yeah, so it solved the problem, but it was not nice since we were not able to generalize it for a longer cycle. And recently, Liditsky and Fender provide characterization of all external examples. So now we know not only the asymptotic value, but really the value for each n and characterization of all external examples. Yes, so recently, together with my PhD student Bartek Kielak, we generalized this in the following case when we forbid odd cycle of length k minus 1 and k minus 2, and we maximize cycle of length k. Yeah, so we did it for all k at least 7. And the nice thing is that this is not flag algebras, it's computer free. It's just by some simple counting. So it occurred that the problem for pentagons was far harder than the problem for longer cycles. And somehow community was focused on the easier case, the smaller case, and it appeared that this was the hard case, the longer cases were easier. And we have a conjecture that for any other setting here, I mean, both integers are odd, and the maximizing graph is longer than the forbidden cycle. Then the asymptotic value is obtained in the balanced blow-up of a cycle, which is like 2 longer than the forbidden cycle. Now you can imagine, for example, if I forbid triangle and I want to maximize 7 cycles, then blow-up of a 7 cycle is not good. Blow-up of a 5 cycle is better, because in the blow-up of a 5 cycle, you can find a bit more 7 cycles, right? And this is the conjecture that we are stating. Are there any questions for the dense setting? Seems not. So let me move to the sparse setting. And the sparse setting, as I said at the beginning, is far harder. So in the smallest case, now maximizing triangles, but they forbid pentagons. We had upper bounds which were consecutively improved, and the best result now is the following: some constant times n to the power 3/2. And the lower bound constructions are the same order of magnitude with a bit smaller constant. So we know the order of magnitude, and there is a small gap in the constant. And this can be generalized for forbidding higher odd cycles. And still, as I said earlier, we get some bounds which depends on the Turan problem for even cycles. So they were improved consecutively by Jerry and Lee, Allen and Schickelman in the mentioned paper, and by Firedi and Teskaya. And so basically, if we solve Turan problem for even cycles, we'll get improvements here. Wishboina and Shapira in the same paper, I already mentioned, the one that provided order of magnitude for all cycles. They found the bounds in case of triangle, but with forbidden even cycles, also depending on this Turan number of even cycles. While in the even setting, we are not maximizing triangles now, but 4 cycles. Even more is known. So we know that by Gerbner, Jerry, Metupo, and Wieser, what's not only the order of magnitude, but also the constant, right? So we know the asymptotic result. There is still some gap here, but it's lower order term, which gives us the asymptotic solution in case of 4 cycles.
Andrzej, sorry, again, a quick question. So when you say bounds depending on this value, extreme value of n C2L, do you mean that if we determine x of n C2L, then we also get the asymptotic for the other side? Or do we get better bounds for the other side, just without at least the order of magnitude?
Yes, so let me say it this way. Upper bounds are given by upper bounds on Turan number. So we get some function of this x and C2L. So if you improve it, you'll get improvement on upper bound. And lower bounds are coming from some changes in the constructions for also extremal number of C2L, right? So it may happen that if, after solving Turan problem for even cycles, that the solution is so strange construction that you cannot extend it in this setting, but all the known constructions can be extended now, so they give us lower bounds here.
Okay.
I hope it answered your question. Yeah. Okay, so we have this solution for C3 and C5 case, and you can see that it's hard. And in the symmetric case, C5 and C3, it was hard, but for longer cycles, it was easier. So one can naively think that maybe if we consider longer odd cycles, it will also appear easier. but it appears it's true. So with my master student, Mateusz Górski, we were able to solve this problem in the next case, which is forbidding 7 cycles and maximizing 5 cycles. And we obtain a result which is not only asymptotically good, but it gives us like exact value without any error term here. This assumption n at least 9 is needed because for smaller graphs you can just take a K6 and it has bigger number of 7 cycles than the construction. Yeah, and what's the construction? So I take a triangle, so as you can see here in the top layer, and then n minus 3 vertices, n minus 3 vertices in the bottom layer, which form an independent set, and they are fully connected with the triangle on top. Now, if you look at this construction, then any odd cycle needs to contain an edge from the top triangle, right? Because except the top triangle, it's a complete bipartite graph. And now if you want to find a 7 cycle, you need to use this edge, and you will not have enough many vertices in the top layer to fulfill a 7 cycle, right? So there are no 7 cycles. And there are many 5 cycles because we can choose like basically any 2 vertices in the bottom layer and complete it with 5 cycles. And this gives us exactly the number here. Yes, so this is the construction. One thing would be in the other cases. And we have a following conjecture. So if you forbid L cycle and you want to maximize K cycle, where K and L are odd and K is smaller, then the best is to take the following construction. We take a clique in the top layer, which is of size L minus 1/2. And all the remaining vertices are forming the bottom layer, which is an independent set fully connected to the clique on top. Yeah, so similarly, this graph will not contain odd cycle of length L, and it will contain lots of odd cycles of smaller lengths. Yeah, so this is our conjecture. Okay, so let me just quickly say how one can prove it, since the time is passing fast. One can think that with this construction in mind, that the best is to pick up a vertex of minimum degree and then prove that it appears in at most 6 and minus 24 copies of C5. This number comes from we would like to use induction, and then this is the difference between the number for n minus 1 and n. And the similar idea was used in the similar problem for puffs, and they have also the same extremal construction. But the problem is that if a graph has big minimum degree, there is a path of whatever length we want, but there is not necessarily a cycle, right? So this approach was good for paths, as in the written result, but it's not very good for cycles. And moreover, the question at the beginning is not true. So there are graphs with a property that each vertex appears in more than 6 and minus 24 copies of C5. And it's not the case of those small numbers, up to 8, but even for larger. For example, you can take 2 K6, and they have each vertex appears in a bigger number of 5 cycles than the conjecture here. So one need to do something different. So what we did, let me define one thing. I would say that the vertex is locally minimal, it has minimum degree, but only among vertices of distance of most 2, so in a small neighborhood. And what we are proving is that a graph which does not contain 7 cycles, and if I take a vertex which is locally minimal, then this vertex appears in one of those special graphs below, or it appears in at most 6 and minus 24 copies of 5 cycles. Yeah, now we can imagine that this can be proven inductively because if I take a vertex of a minimum, which is locally minimal, then if it appears in a small number of cycles, then I can just remove it and continue. And if it appears in one of those special cases here, then I need to just analyze the neighborhood and see that the number of vertices in my graph needs to be small, which gives us those small cases up to A. And if it's bigger, then we get some sort of contradiction. Yeah, and this is enough to obtain the wanted value. Okay, my time is over, so I will probably not explain more details of the proof. Thank you very much for listening, and I hope you will enjoy the rest of the mini symposium and of the conference. Thank you very much.
Thank you, Andrzej, for the very nice talk. I think we have, or we take us the time for one question at the very least. Are there any comments, questions for Andrzej?
Actually, I have a tiny question. So is the problem for path solved in general? So you cited this particular instance.
So for paths, it's known order of magnitude for every length of the path. But in case of specific lengths, we have either, like for maximizing P4, we have exact result. And for maximizing probably P6, we have asymptotic, if I'm not mistaken, but for longer, we don't have the order. We have order of magnitude, but not the exact value. But I would need to check to confirm it.
So possibly following up on that. So you do the induction and then you have the 6 special cases. Yep. Let's say if we now have not 7 and 5, if we have something bigger, do we potentially expect to have more of these exceptional cases where we have to actually look at the structure very closely? So general case might then be
I think
feasible by induction.
Cases would not be hard because there are extremely dense graphs, and then those vertices cannot appear in I mean, if this is V, then those other vertices will not appear in some 5 cycles outside, because you can close 7 cycles using the structure here. Yeah. So for longer cycles, you can also do it. The problem is with this induction step that if you have a minimal vertex, which is quite big degree, then you need to somehow control what's going on around. And this is quite technical to see that you can always like cut off some part of the graph, which appears in at most 6 times the size of the cutout part to obtain a smaller minimal example. Yeah, so what I want to say is that if we consider longer cycles, then it's just longer analysis, and I'm not completely certain that one can complete this analysis. This paper is already quite long, so it may be hard. I think one needs to do something better for longer cycles.
Okay, yeah, thank you very much indeed. So then I would say let's have a 2-minute break and start at 52 for Bjarne Schülke.